Well, good morning. We're waiting you. Okay. So this is our last week of lecture. Okay. So here's the plan. We are in week 15. Okay. A and B. We are going to have 2 lectures this week. Okay. And next week we have no class. Okay. No class. However, I'll try to be here or in my office or in the lab, try to have one-on-one meeting, okay? Okay, one-on-one meeting, discussing about your FISP, okay? And according to my schedule, we're not going to do FISP presentation, okay? We're not going to do no PPT presentation. Okay. No. So, but we are going to have a self-recorded PPT plus voice and movie format, so that I can put into the YouTube using this one. This one. According to our schedule, today. Okay, so next week we have no formal lecture like this. So I'm going to have another lecture this Wednesday. So today, what we're going to do is a few things, okay? Some of you, okay, I know some of you, not all of you, may not have basic fractional order control, okay? Fractional order modeling basics. So I'm going to give you the basics, okay? The first part, okay? First part. So I'm going to show you what is fractional calculus, what is fractional order control, how to discretize it, how to implement it, okay? So that's fractional order model. And then the second one is and fractional order control, and what is the connection to the robust control? Okay, okay, robust control. We are going to have what I recently invented. If we go back, we are going to have a Bode's ideas. I'm going to introduce these things. Nobody will cover in the text. In a classroom setting like that, I'm going to talk about this. So the first idea is called Bode's idea crossover. Okay? Crossover. The second one is called Bode's idea cutoff. All these 2 things are very useful in our robust control connection. Okay, robust control connection. So these are the one aspect. Another aspect is regarding what we call Flatphase idea. Flatphase. Flatphase. Okay, Flatphase idea. So you design such that the phase of the crossover is flat. Okay, it's flat. So then we can extend this one. Extend to loop shaping involving fractional order control. Okay, loop shaping. People are already talking about it. If you Google the fractional order loop shaping, they are still. So these are some ideas, some future work. Okay, future work. So today we are going to cover all these. After this one, you can say, I got a formal education from classroom setting that I can do fractional order control. fractional modeling and do robust control based on fractional calculus. I'm going to show you that the idea could be traced back to Bode's ideas. Okay, Bode's ideas. So I'm going to do step by step. So step by step. First of all, I'm going to do some slides to show you how we can do the modeling. So what is fractional calculus? So fractional calculus is you do d dt to the power of alpha, okay? Power of alpha. While alpha is a real number, or alpha could be a complex number, right? Complex number, okay? Complex number. So people do this one, you can write down this d alpha, dt alpha. You can do that, okay? You can do that. So this is for sure correct notation. I want to mention that, what if you have something, you have alpha 1 here, alpha 1, 2 here, is this illegal? Perhaps not, okay, perhaps not. So at least I know that there's something called d dt alpha. There's no alpha in here. Okay, so that is called a fractal derivative. Okay, so fractal derivative. We all know that any x dot is minus x, x. Okay, so the initial value will be x0 and e minus x. Okay, t, that's x of t. So this is called exponential law. Exponential law. So how I can have something like x of t is somehow like t to the power of alpha. Okay. How we can is instead of using this one, so this will need fractional calculus and fractional differential equation, something like that. X. Okay. I use this one is to approximate. It's because of the asymptotic behavior of multi-vector function. So there's some details, but you can ignore that. So actually there should be minus alpha here if alpha is positive. Okay. Most recently I said that I have a decay ratio in here. So it's exponential here. You have exponentially decay. Then you also have this is called algebraic decay. So they go faster then slower. Okay. But there is something in between. In between is something called e to the power of minus lambda t to the power of beta. Okay, so this is called a stretchy exponential. So you got two tails. One is exponential tail, algebraic tail. Exponential tail is integer order differentiation. Algebraic tail is fractional order differentiation. But sometimes I need something in between. In between. So what that is? So that's something like this. Okay. Something like that. So this is something called in between. Okay. This is called stretched exponential. Stretched. Okay. You have a beta. You can tune the tail behavior. Okay. Tail behavior. So it's like we have two totally different words. One is integer order words. One is fractional order words. Well, what's in between? Is there any bridge in between them? Now I start to believe that yes, it's true, like that. But what is this one corresponding to what kind of differentiation in here? Yes, there is. So this is a recent book is called Hausdorff derivative. It's actually a more general case like this fractal derivative. That shows alpha is here and this is a 1. But I believe in general you can go from here. Okay? But a lot of physicists do not like that idea. They say, hey, you do this one, you mess up my dimension. Okay? So what is the second? Okay? I have a second, which is a dimension. Well, what is square root of my second? Okay? Make sense? I think this complaint is valid. But what if I say that I assume my t divided by characteristic capital T and make it tau? So the tau is dimensionless. I don't have a dimension. So then whatever power you put here doesn't violate anything, isn't it? Yes, that's how we should look at it. Don't get bothered by people saying that, hey, you have problem with your dimension. You don't need to bother because we're working with dimensionless variable. Make sense? Okay, so I hope you have understanding about fractional calculus, fractional derivative. So here is something I call tail management or tail characterization, okay? Tail tuning, okay? You can tune the tail, okay? You can tune the tail. So better you have two separate words. One is exponential. You have a different time constant in here, so you can change the tail behavior. Or you have an algebraic tail, you change the alpha, you can decay differently. But to me, these are two separate words. One is integer order, one is fractional order. But there are some things should be in between, continuously tunable. Therefore, we should respect this type of fractal dimension or host of derivative. Host of derivative. We have that book here. I wrote book review. I'll send to the class. I also have a piece of code I wrote to plot this, so you can have a look. Okay. So that's a fractional calculus basics. So we are not mathematicians, so we are engineers here. I agree. So we only need to know that the Laplace transformation, that you have d dt, you get s, right? So, or in other words, you call Laplace transformation pair. So you have f of t, then you have f of s is a Laplace transformation pair. Then you should know that dt f of t, you will get s to the power of fs. Of course, we assume that 0 minus all 0, all initial values are 0. Okay, initial values are 0. But regarding initialization, there's a very lengthy discussion about it, how to assign the initial value. So there are two things we should bear in mind. In engineering, okay, in our field, I suggest everybody focus on Caputo derivative. Okay, Caputo derivative. The reason is then we can set up the initial condition the same way as integer order case. And of course here alpha can be imaginary number or can be a negative number. So negative number. So Caputo derivative is from this point of view. So say for example, you have a f of t. What do you do about alpha is 0 to 1? You do integration. This is defined as convolution of this f of t, right? Okay, convolution f of t. So then Riemann-Liouville is doing this. So this the d, the dt, I, alpha, f, t. Okay. okay, is defined as the d 1 minus r, okay? Right? So this is, you do a fractional order derivative first, then you do this. So this is a Riemann-Leibniz case. Riemann-Leibniz case. On the other hand, you can do this one. You do derivative first, then you also write, okay? Right. So this one will give you capital sense, okay? So you do integer order derivative first, then do fractional integration. So there's a difference, okay? There's a difference. Okay? So I suggest you focus on this one in our engineering subject there. Okay? We're not doing a lot of abstract math. Okay? So it's Caputo, so Riemann-Leibniz, okay? So with that, we quickly can understand that you can generate s to the power alpha, and you can write down function of g s, okay? You replace s with s to the power alpha, okay? That's alpha. Then if we write down, can you take a picture? Then I'll erase everything.
Do we need weighting function on the convolution? Gamma?
Yes, the gamma one.
Yeah, I think I lost the gamma. Okay.
Gamma alpha.
Okay. So yes, we need that. Yes.
Yeah, I think it's
Um,
gamma.
Okay. Okay. Good catch. Good catch. So the point here I'm going to make is so in the integer order case, I have a transfer function. Okay? So we assume that this is g of s and m less than or equals to n. So that is our case. But now replace s to the s alpha. So I have alpha here, I have alpha here, alpha here. So this one is called commensurate order. Commensurate order. So you have a single base order s to the power of alpha, right? S to the power of alpha. Okay? All right? But it is interesting that it's possible I can say, hey, s to the power of alpha sub k, s to the power of beta sub k, okay? So in previously, alpha k is k times alpha, beta k is also k times alpha, right? So that's called commensurate order. But if I write it in general like that, it is not commensurate anymore. And how to check the stability of this one? If you have an idea how to solve all the roots, and the roots is on the left half plane, of course, it is okay. But in commensurate case, so you can always say, let's say alpha is from 0 to 1, so then you replace this one and get this. So this is a real part, imaginary part. Suppose alpha is 0.5, then you have anything inside here is okay, meaning you are assuming that AK, like WK, and sigma BK, oh sorry, this is BK, okay. BK, WK, okay, K is 0 to N, K is 0 to N. So then here, W is S to the power of alpha, right? So basically this is the W plane, okay? This is the W plane. W plane. So we are checking the roots of the W plane, whether they live in here. Okay, live in here. So this is called the stability region of this commensurate fractional case. But usually we use something called argument of my the roots Wi, okay? Okay. So meaning if we have a root in here, then its argument means the angle is complex number, right? It's supposed to be. So if it is greater than this one, greater than this angle. So this one argument of Wi is greater than this angle. This angle is 2 pi times alpha. So when 2 pi times alpha. When alpha is 1, then this red line will be an imaginary axis. Okay? So it's something you can write this way, and sign this way. Okay? So kind of like you bend the imaginary axis with the angle here. But your stability and the root here, the angle should be greater than this one. So that is a stability condition. Okay? Stability condition. So that's the point. But on the other hand, people feel like even in the simplest case, 1 of s to the power of alpha, the fractional order integrator, how I can make this one into approximate digital IIR, okay? Infinite impulse response, meaning you have a z minus 1 and b z minus 1. These are polynomials of z minus 1. So if you have a polynomial like b, so if the b, this one is 1, then this RIR becomes FIR, okay? Finite impulse response. Okay, finite. So if you don't have denominator, then this is a FIR, okay? A lot of people doing FIR. I don't like FIR because FIR you need a very long order of this to approximate this. While you use IRR, you have a smaller order of A and B combined, you can approximate this very well. So if you use a short memory principle and truncate using a Gromov-Litvinnikov finite difference approximation, that will lead to FIR, okay? Gromov-Litvinnikov finite difference approach, okay? So, but I think in the early days I did a lot of work in the IR approximations, more economic, okay? But in general, we can have something like that, okay? Something like that. So then, if I say I have an analytic impulse response, and here I also have a GT here, if these two are the same, okay, are the same, it's called what? It's called impulse response invariant. Okay, then we turn this one into, this one is like S to Z, right? So this is called discretization. So I invented, this one is called impulse response invariant discretization method. Okay, method. So you guarantee that after you do the approximation, this guy's impulse and the analytic impulse in here, okay, they are the same. They didn't change. Okay, they didn't change. That's very good, isn't it? If we can do that, it's very good. Consider that a good approximation. Okay, so I'm going to tell you that the key question is, given this, how you can get this one. Of course, in this case, we do know they derived fractional order integration. What is the impulse response of that? Okay, we do know the analytical solution for that. But in general, what if you don't have? So let me tell you something. Say for example, fractional order PI. Fractional order PI. So I'll have fractional order PID. So this is like a C of S is KP plus KD S to the power of lambda plus KI S to the power of mu. Okay, so that is lambda mu is between 0 to 1. So you have 5 parameters. Okay, 5 parameters. 1, 2, 3, 4, 5 parameters. And how to tune them. Okay, how to tune them. So you can do optimization. There are some codes you can do the work. My point is, if you know how to do this one as AZ, BZ, approximation, if you know this one, how to do AZ, PZ, so then done, right? So it's pretty straightforward. Okay? But remember, you want to have AZ, BZ, have this one. You say that, oh, can you say that, in this case, can you say that S alpha is BZ minus 1 divided by AZ minus 1? Can you simply do that? Be careful, probably not. Because this guy, in this case, this guy must be minimum phase, meaning there's no zeros outside the unit circle. Otherwise, if you do inverse, this becomes unstable, right? So how you can approximate and guarantee that this is stable, of course, at the minimum phase. So stable at the minimum phase. And minimum phase approximation. And basically also I hope is impulse response invariant. Okay? How to achieve that? Okay? How to achieve that? Yeah, I figure out some ways. So I don't think in the literature people put emphasis on all of these features we want. Okay? So we can do that. I'll show you the code in a moment. Okay? My question is, this is a simple case. I want to make your life a little bit different. Okay? So, so in the literature we have FOPI. Okay? So it's called C of S is a KP plus KI S to the power of me. So this is FOPI. But also we invented something called FO graph PI. Okay, graph PI. Okay? That means what? The C of S is KP plus KI, but this is 1 over S. Okay, 1 over S is integer order. Okay? However, I put this one bracket together and to the power of mu. Okay? So we still have the same tuning knobs, 3 tuning knobs. Okay? Now question is, which one is better? This one is better, or this one is better? In what sense? If you can answer this question, you can write a good paper. I know we are writing. Well, I want people to answer this question. So naturally, you can ask this question. What is FOPID then? So we can write down what format? It's KP plus KDS plus KI. Then we'll put this one to the power of mu. Okay? So how many parameters? I only have 4. 1, 2, 3, 4. Okay? I only have 4. My question is, can you prove or disprove that this is better than this? So this is 4 parameters, this is 5, okay, remember. So if you say, oh, I use 4 tuning knobs, I can do a better job than 5 tuning knobs. That would be wonderful, isn't it? Yeah. We haven't write this paper yet, so you have opportunities here. But now, question is, given this one, how you can approximate into AZ minus 1 and BZ minus 1? How? And still, I hope this one impulse response invariant discretization, and I hope it is stable and minimum phase. Okay? Stable and minimum phase. Okay? That would be nice if we can do it. Okay? Yes, we can do it. So what if I say, what if I can, I forgot to mention. So let's say, what if I can do x plus iy, so complex number. So 1, 2, 3, 4, 5. So I have 5, so then this can be this one. That shows some benefit of using integer. So, but again, how to do that, okay? So all these questions are not very well answered, okay? Yeah. So I need to teach you how to do this, okay? Okay. But obviously we don't have time. I'll point you to the right direction. You can explore if you want. But the question is, you need all this freedom for what? Okay, for what? You have fractional order. You bring in fractional order. It's supposed to be better. In what sense? What sense? For what? Okay, for what? So I think eventually, I think there are two things. One is called stability. One is called performance. And both of them, we need robustness. So this aligns to our ME course objective here. Okay, objective here. Okay. So I'm going to go through a little bit here, then I'll continue to talk about all the ideas. Okay? All the ideas. So before that, I want you to think about the following question. Okay? So the following question is called, you know that from Bode's integral, Bode's gain phase relationship. You heard about this one, right? Bode's gain phase. So you have phase, then you know the gain, you have gain, you know the phase, you only need one. Make sense? So of course for minimum phase system. So what if my gain is doing this? Then what about my phase will behave? Okay? Then, if my phase doing this, and what are my gain should behave? So I think this can be induced from this equation. I hope you can think about it. So in this sense, I call this is Bode's step. Bode's step. Okay? It could be a gain step, it could be a phase step. Okay? So a gain step and phase step. Okay? What I suggest in previous time is a phase step. Say for example, I have a phase. I have a phase initially is 0 and come to here. I have a step in here, so this is my phase. Okay, I keep it like flat. It's like phase step in here. Keep this step, and so then I can claim that within this range, my system has certain robustness to the gain variation. So let me give you a picture. Let me give you a graphic explanation. Okay. say for example, you have a gain crossover here, okay? The phase is, this is like minus 180, minus 90. So initially the system is 0 degree and it's passive. You're going down and going down. So it's something like this. So this is your phase margin, okay? This is your phase margin. Corresponding to that, okay, gain crossover, the omega gain crossover. So then this is kind of like a step or flat, okay? Or flat in the phase. So then we can simply say, oh, at this point, we have peak point in here. So this is a loop gain is G omega times C J omega. So then basically here means that D omega, okay, this is my omega, okay? D omega. And this is argument of my LJ omega, okay? Do that, and when omega is omega gain crossover, when this one is 0 means it's flat, okay? So this is called flat phase condition. Flat phase condition, okay? Flat phase condition. So why this is important, flat phase condition, is because if you somehow you have some sort of system, you have LJ omega becomes K times LJ omega. So this is K is called gain variation. Gain variation. So if you do log, so this K, usually the log 10K is 0, 0 dB, right? So this is K is 1, okay? You didn't do anything. This is nominal. But what if you have a K like 50% more, 1.5? Then what are you going to do? You shift log 1.5, right? So you shift this one. Okay? You shift this one, right? So if you reduce, so there's a 0.5 to 1.5, you change. Then I have a band in here. So in other words, your gain crossover is here, or here, or here. This is nominal. This is corresponding to here. This is corresponding to here. So in this range, your phase margin is all this way, okay? It's almost constant. It didn't change. It didn't change. Therefore, I say my system transient behavior is linked to phase margin. So my performance stability margin is independent, almost independent to your gain variations here. Isn't this robustness? Mm-hmm. Yes. So it's called robustness, flat phase idea. Okay, flat phase idea. Okay. So that's the key point of our development. We add this as extra constraints to tune our controller that we achieve this type of flatness. Let me show you one slide. So this is exactly the same idea. I have a simple first order plus delay system. First order plus delay system. So the basic setup is like this, okay? Really. Okay. I want you to see carefully regarding whether we have the gain phase robustness. So I'm going to so you can see our plant is like that. First order plus delay. First order plus delay. We have integer order 3-parameter system. We have fractional order also 3 parameters. Okay, 3 parameters. So what we introduce is exactly this flat phase idea. So you have gain crossover in here. So if we have gain variation, then your Bode magnitude plot is going up and down, up and down. Then your omega g gain crossover will change left and right, left and right. So this is my phase. So I maintain my phase like a step in here, okay, like a step in here, okay. So that the overall system is robust to gain variation, okay. So that is 3 design parameters. Gain crossover frequency, you can tell me what do you want, omega c. Phase margin, how much you need. And flat phase is imposed. 3 conditions, you tune the 3 parameters, like the 3 parameters here. 1, 2, 3, and 1, 2, 3, okay? So we do the simulation. This is the one I want to show you. So if you design Bode plot for Zyglos-Nichols tuning rule, so this is the original system, integer order, okay? So this is also integer order, but compared to Zyglos-Nichols tuning rule, we impose the flat phase condition here. So this is the gain crossover, so this is 0 dB, so this is the gain crossover to here, look. You impose that, you can see the phase will behave differently, and magnitude is different, okay? So what is the original system, first order plus delay? So you change the gain plus or minus 40%. The red one is nominal performance. The black one is reduce the gain, the system will be slower. If you increase the gain, the system will be, okay, almost unstable, it's very oscillatory. So the gain crossover here, phase crossover is here, and gain crossover is here. So then you can hear you up and down, so the phase margin will be changing a lot, okay, changing a lot. So this is something we don't want. My system performance is not gracefully, gracefully decaying, no. So it's one side is getting worse, one side probably is getting better, okay? So the red one is nominal. So while if you impose the flat phase in here, okay, flat phase in here, so then you will have very gracefully degrading of your performance. So this is nominal, is red. Black is you lower your gain. You increase your gain. See, you have certain this overshoot is almost the same. So that's exactly due to the phase flatness. Okay, phase flatness. Make sense? Interesting? Yes, very interesting. Yeah. So this is only for integer order, okay? Only for integer order. For fractional order, we have more things to tell, but I'm guessing I'm running out of time. Okay. So the flat phase concept I already told you. So next I'm going to show you something that is really interesting. It's called Bode step. Don't get very confused about this figure. They follow my pointer. Basically, they say that for Bode, for the loop, ideal loop shaping, you should have a crossover rate here. This is the crossover slope, okay, crossover slope should be like less than an integrator, double integrator, less than a double integrator, and then you should go a step in here roughly. Then you roll off steeper, high frequency asymptotes, a little bit steeper. So this basically is the one Bode suggested. Okay, so if you have a motion system, what's the open loop? It is minus 40 dB per decade. It's a double integrator. You have two integrators. He said that you should go double integrator, but then you should cross over this one, and with like 1.6, I remember, 1.6 order. Okay, 1 over s to the power of 1.6 to cross over with that reduced rate. Then, after that, you should just further keep it flat for a period. Then you go down very aggressively. So that's what we call asymptotic Bode, using a Bode step concept. So I think this is not widely known. This is a principle of how you shape your loop. So basically he said you should do this, and this is the original system, and you make it crossover here with a slope of 1.6 order. Then you keep it flat for a period, then you go down very quickly. So that's called exactly the same. So based on this principle, Boris Luria wrote a paper called System Architecture Traits using Bode step control design. So this is, to me, is a new framework of design control system. But it's kind of like a precursor concept of loop shaping. When you do loop shaping, what is the ideal loop shape? Okay, Bode already gave an answer. The loop shape should be like that. So then he designed this controller. So basically you have a double integrator, you have this one. So then they did a normalized open loop response. So, I did something here. Then let me go through here. So you can see that this is the original system. When you do the crossover, it's 1.5, okay? And when go down, it's 2.7. That's using what they described in here, okay? So this is the phase. You can see this is the phase margin, okay? Phase margin, and you can see. Can you see that this phase margin and this crossover frequency is here is flat? So what do we say? So it means to really achieve the flat phase, you should use a step in here. And maybe it's a coincidence. So, maybe it's a coincidence. So if you need a step in phase, you also need a step in Bode magnitude. So this is a step, you also have a step in here. Make sense? Very interesting? Yes, very interesting. Very interesting. So I think in summary, I have introduced this connection to the robust control problem, talking about magnitude step and phase step and flat phase concept, robustness with respect to the gain variation. So that's this Nyquist plot. So Nyquist plot here. So there is a period of time in here. This is vertical. When this is vertical, it's an iso damping property. Okay, that means your step response, the overshoot will keep the constant, will not increase or decrease. Okay. So with that, it's time to tell you the secret ingredient in here. So how you can approximate 1 over s to the power of alpha? there are many papers doing that. So if you draw Bode plot for s to the power alpha, it's perfectly fine in MATLAB. So I did it in, so this is 1 divided by 1, 0, so this is 1 over s. So this is 1, 0, SSL, or 1 divided by SSL, so it's, this is s. So this is s, this is integration, this is a differentiation. Differentiation has a 90 degrees lead, this is a minus 90 degrees lag in phase, okay? So, but for fraction order, it's perfect, it's okay. So you have a half integrator, you can do that. Remember, so this is a 0 to 1. So this is called 1 decade. 1 decade. Let's say from 1 decade you get to 0 to minus 10 degrees. So the slope is called minus 10 decade per, minus 10 dB per decade. Okay? But remember here, so you have, this is a 1, this is 0 to 1, so this is a 1 decade. So this is a 1 decade from 0 to minus 20. So slope of this guy is minus 20 dB per decade. So it is different. Okay, it's different. So you can draw this figure using this simple thing here. But how you realize it, there are multiple ways to do. People using RC networks, you go infinite as many as you can. So you get the minus 45 degrees, the phase. There's a minus 10 dB, minus 10 dB per decade. Okay, so let's see, this 0 to 1, so this is almost 10, yeah, it's around 10. So, in fact, the key point is we can use analog discrete components to approximate that, but later on, Gary Bohana invented something called a Lossy capacitor. He called it fractal. We patented it and gave us a presentation. This is Ivo Paoludni and Gary Bohana. This is a soil physicist, and this is a PhD student. So you can see basically if you put this capacitor in here, so you will form a fractional order integration. And we did experiments about fractional order integration. So this is op-amp, operation amplifiers. So you can do this one, do a lot of testing like Bode plots and check. So then later on, we put this one into a chamber and cook it, heat it up to see how the lambda is changing, the order is changing. It turns out that the order is a function of capital T, temperature. This is natural. So then we can say, oh, I have a dynamic system whose order is not integer, while the order is dynamic changing according to another dynamic system, which is a temperature control system. So in other words, I have a dynamic system with a dynamic order. Make sense? So it's very interesting. Now I already told you that we can do this, okay? So there are two ideas. One is to approximate in continuous time domain, but with this one, you can still use it, like using C2D discretize this one. But what if I can do this one direct to Z? That would be nicer, isn't it? Okay. So this is called all-stop recursive approximation code. So you go to MATLAB Central and you get this code. I wrote this code a long time ago. So then basically you have minus 1 over s to the power of 25, half order integrator. So the phase will be minus 45 degrees. The magnitude actually is this one. So this is a whole integrator, okay? The red line is whole integrator. All-stop will be this dotted line. Okay, this dotted line. So it's a minus, so it's kind of frequency banded within a certain frequency range. You specify it, it's called omega L and omega H, low and high, inside the frequency range of interest. you do approximation, and you don't care what's outside. The basic idea is from this one. So basically, you have a line that is not 20 dB per decade, okay? But you want to use, these are 20 dB per decade lines, okay? So these are integer orders, okay? So then I call this a zigzag line to approximate this line. Well, this line is not 20 dB per decade, okay? So then because of this lead lag, then you will have phase modulated something like this. So in average, you have fractional. Right. So that's the basic principle. So in fact, by doing that, this one has a product of poles and zeros, simple pole, simple zero, no multiplicity. And they are interlaced very nicely, recursively. Then it is also minimum phase, so, and stable, okay, stable. I invented this code. I wrote this code. So you can just give order, this is 0.01 is your sampling period, okay? Sampling time, sampling period. Then this is the order of this polynomial. So they will do an impulse response invariant discretization for fractional order differentiation. So you put a minus 5.5, this fractional integration is the same. So what you are going to get is, the red line is the true for half integration. So you have analytic impulse response. The circle is approximated. So you can see they are coincide. So that's why we call it impulse response invariant. It didn't change. However, in frequency domain, the red line is the ideal, while the black line is the approximate. And it's like kind of approximated in a limited frequency range. But this is Nyquist frequency here, so it's already pretty nicely fit. Okay, it's pretty nicely fit. Okay, so remember, you can your system sampling period is 1K, 1000 hertz. Okay, but now you can do a good job within 1 to 1000 hertz nicely. So I think those differences is okay. Okay. So the question is, we happen to know the impulse response in here, but what if we do not know? Like, so what idea is, basic idea is simple. Say for example, I have a PID is integer order. Then we do bracket to the power of alpha. How we can do discretization? If I don't tell you, it's difficult, and nobody really can do. However, using my method here is, you generate impulse response using a numeric inverse Laplace transform. So then you get impulse response. Okay? Then you use Prony command in MATLAB to get this. So this is the Prony technique. Digital filters. So if you have impulse response like this, you will be able to get this RIR approximation. So basically, can you see that this is FIR, right? This is IRR with finite order. Okay? How you can get that? So there's a code to do the job. Okay? And in general, I said impulse response, but what if I have real input, real output? Like step, like sinusoid, you get another output. So from in and out, can you come out that as well? Yes, this is called Stieglitz and McBride iteration method. So the code is there for you to do the job, okay? So that's why in the code, sometimes I say, oh, let's do step response invariant approximation. Can we do that? Yes. So we have two commands that can do the job. Okay, can do the job. So you can see this is the Prony command. You give the Prony impulse response. You give a numeric order and denominators polynomial order. It will give you numeric denominator and numerator denominator coefficients. Okay, so it's pretty. So if you have an impulse response h of n, you will be able to get this. Okay. And the other one is called
STMCB.
STMCB.
Yeah.
STMCB. Okay. STMCB. Very good. So in here you are going to get. So you are going to get B and A is the coefficient of numerator and denominator. Okay. So what do you get? You can do an impulse response here. You can give impulse. Okay. Or you can give input and output x and y, and you give a numerator and denominator's order. So they will get you this. So it's more general than Prony, okay? More general than Prony. Okay. So the details are published in IRID transaction here. Automatic control, not signal processing. Interesting. So let me go back to this one as quickly as possible. So this is called discretization. I think you have no problem to do that. I want to go through one of the codes with you called impulse response invariant discretization of complex fractional order integrator. So you can download and you can play. I taught Zheng to put this one in, and this actually just updated 2 weeks ago. Okay, you can see. Okay. We submit this paper to. So you can see there is there's a archive paper corresponding to that. So then archive paper will refer to this code in here. So then you will increase your impact of your work, right? So people will be able to do that. So what they do is the code, IRID, fractional complex order integrator. So this is the real part, imaginary part. This one means, let me see, I forgot. One means the time, okay, the time length. Oh, sorry, one is the gain crossover frequency. So basically we're talking about 1 over s. But usually you should say 1 over s to the power of x plus iy. So, but sometimes people may say, oh, no. Well, we should talk about j omega divided by omega 0 and to the x plus iy. So this omega 0 is somehow like a crossing frequency. So when omega equals omega 0, this is 1, right? So 1 then is a 0 dB. So that's the frequency you cross that real axis. So of course, usually you can using omega 0 is 1. So then you just normalize everything here as a k, okay? So that's the way we so that's why we can say this omega 0 is 1. Omega gain crossover is 1. Then we talk about time range, then frequency range, then what's the order? So this is the order. Okay? This is the order. So you can go here and take a look. These are the codes. So these are the codes. Okay, they give you two LTI objects. One is discrete, AZBZ. One is ASBS. Okay, A of S, B of S divided. So then usually when you write a code for a lot of people, general purpose, you should do all the argument tests. You check how many arguments and some default values. And then, so all these are kind of arrow checking about how many you put in. So these are very safeguard, very important. But actually what we really need is NILT is a code you can download from also the web. Actually, he probably used NILT. No, he didn't. So he said NILT was obtained from here. NILT.m is from here. Okay? So you can download it. So NILT is you give S. This is omega GC is your gain or crossover frequency. So when S is omega GC, then it's 1. Then this is to the power of lambda and cosine mu log omega S. So this equation, you may wonder why this is the case. You can read the paper here, okay? You can read the paper here. So why, this is based on previous discussion how to define the complex order derivative, okay? So with very complicated commands, so, but doesn't matter. We just give this one to NILT, then we will be able to get impulse response FT, okay? So the T1 is time, FT is the impulse response. So this figure gives you, NILT give you analytical impulse response. Then, of course, then this use STMCB. But in this case, you can use, of course, you can use what? Proning. But STMCB is more general, okay? So then you get the order, you get this numerator denominator. In this case, numerator denominator, you get a transfer function here. And this is your time, And then you get a GD. So this is, then D2C, you get GC, okay? D2C, the discrete, so this GD is discrete LTI, so D2C is discrete to continuous, you get GC. So from here, all done. Actually, these are a few lines already done. The other is just visualization, okay? So this discretization can be really made simple if you have NILT. So let me just remind you that it's simple. Basic idea is simple. Generate your response analytically, so you can use prime. Then you can compare compare Bode plots, compare step impulse response, and so on and so forth. Okay. So our timing is good. So before the end, so these slides I'll upload. You can take a look, okay? But our goal is today is to explain the following. As I told you that you have a Bode step and Bode step, your Bode ideas. So I'm going to tell you what are Bode ideas, okay? I think I already explained to you what is Bode ideas. So Bode ideas is saying that for a nice system, so okay, Bode's idea is basically he said that you need to keep a step in here. It's called Bode step. Okay. And we need to keep this slope about 1.6, okay, 1.6. So what does that mean? Is minus 32 dB per decade, okay? Because otherwise it's minus 40, okay? So I need to double check. Perhaps that needs to be double checked. But Bode in the book didn't specify a fix. He said, for example. I remember clearly, for example. He said, for example, the gain crossover should be in between, like, I think it's in between S minus 1 to S minus 2. So the single integrator versus double integrator. And motion system, so you have mx double dot is f, right? So this is 1 of s squared, so it's this one. Okay? So motion system is minus 40 dB per decade. But he said, no, you should not do that, you should slow it down. Okay? So to like minus 32, not minus 40 dB per decade. Okay? Don't go fast. You can go here like greater than minus 40 dB per decade. So this is called a roll-off. Roll-off. So anything that Bode's ideal 1 is called Bode's ideal crossover. What's the ideal crossover rate? Slope. That is, you need s to the power alpha. In the neighborhood of this, while alpha is between 1 to 2. Okay? Some people say, oh, probably I put 1.6. No. He never defined a fixed value. He said, for example, 1.6. I checked the original text. So this for example. Okay? So that's Bode's idea. You have seen that this step is so important to achieve the flat phase. Although the design didn't follow the flat phase, while we go from flat phase to the design, okay? So I think our contribution eventually meet, okay? It's like Mesa Lab meets Bode, okay? We meet Bode. So in the end product is, when you have a gain crossover, your phase is flat. The phase is flat, okay? The phase is flat. But really, how you achieve the phase flatness, you need this mechanism that is not seen in any textbook carefully, except the Boris Luria and his book. He wrote a book. He also wrote a book. It's called Feedback Maximization. Feedback maximization. I love that. Boris Luria. Okay? Boris Luria. This is wonderful book. But it's not widely read. So later on, he wrote another book. It has second edition. This is a book in 1980s. Okay. He wrote another book. It's called Classic Feedback Control. Okay. Feedback Control. Then there's a second edition based on that. This is the only book in the world I have seen so far that use the same language and symbol as Bode. Okay? To present Bode's integral, and he listed about 20 Bode integral relationships. And we only use one or two of them. There are many others supposedly you will find interesting applications in our future. So then after I finish next one, I'll let you guys go. It's called Bode's ideal tree. Okay? So this Bode's ideal, I explained to some of you, but not all of you. So today I'm going to tell you here. This is called Bode's ideal cutoff. Okay? Bode's ideal cutoff. What does that mean? So you can see Bode's ideal one, Bode's ideal crossover is meaning fractional. Okay? Calculus skill. Bode's ideal cutoff is demanding from this one. Do you guys remember what is a low pass filter? The magnitude? So low pass filter is you got low pass, until to a point is called corner frequency. Omega C, C stands for corner. And then ideally you just go to infinity, become 0. So then this is a log plot. But what if you are doing something like 1, 0? So you basically want something like this. So this is omega C. So you want something like this. This is omega, this is the magnitude. Okay? So you want something like this, right? But you end up, you cannot. So you have to respect. So you got something like this. Okay? And then you are going to have something like this. Okay? So say for example 1 tau s plus 1. Okay? Okay. So then this is 1 over tau. So 1 over tau. Okay, 1 over tau in here. And this, what is the slope in here? It's minus 20 dB per decade, right? But if you say, oh, I need more, don't worry, you can just hang, right? So you can minus 40 dB per decade. But say you say, oh, I don't need this small, I don't need this big, it's too much. I need something in between. Then you need alpha here, right? So in between 1 and 2, right? So that's fractional order low pass filter. And I have code already, this one. How you can do the fractional order low pass filter, bracket to the fractional order, how to approximate to AZ and BZ. It's in MATLAB Central. You search my name, okay? It's there. But my point here is, Bode, he said, well, I don't like this. I cannot do this. What if I can do this a little bit? So can I do this? Can I do this? Come over here, okay? Can I have a filter I can go from here with this corner is 90 degrees? Then for just a period of, then I just come over here. So he said, can I do this? This is called Bode's ideal cutoff. So he cannot do this 100% ideal, but he can do a little bit. Then come down like this. That's called Bode's ideal cutoff. Okay? And what is the transfer function of this guy? I'll tell you. So it's so that is what they call Bode's ideal. But of course, you can put 1 in here. But in his book, in Bode's book, he said, I can add something here. But remember, I have square root of something here. Okay? Isn't this nice? So by doing that, you will have this. Of course, I normalize everything to here. So So this is Bode's ideal cutoff. I already have a paper published on this, at least I got 3, maybe 2, published using this idea. So whenever you can use a low pass filter, using this ideal filter. Because you already learned how to do this one in the AZ, BZ, right? So realization is not a problem. Why not you try it? Maybe you can achieve superior performance, isn't it? So I stop here, it's too much, 10 minutes more. Then, okay, so take a picture, and then we stop here. And I'll upload related slides for you. But I believe this is something that you should feel very excited about it. So just stop here. Thank you. I'll see you Wednesday. I'll be here today, later afternoon. I'll leave my office 2:30.